local fields in lattice models are fundamental as well. Those two being the first two examples. In general, you should think about approximately sort of locally defined random variables. So the spin is one example, the energy is another example, locally defined near the point Z1, for instance, the yellow ones are. And what you do with those is you form expected values. So you take expected value in your discrete domain now of maybe products of such things. Now I'm going to give a wish list. For what I would be happy to call like a description of a scaling limit of a statistical mechanics model in terms of conformal field theory, and then we'll see whether we agree with those wishes being reasonable. Well, I might, since a fundamental structure on the state space is two Virasoro algebra actions, I might hope that I have two Virasoro representations on local fields of a lattice model. This might seem a little bit crazy because the Virasoro algebra sort of arises as the infinitesimal description of conformal invariance of the fields in the continuum, whereas on the lattice we certainly don't have conformal invariance. Turns out that this is not completely ridiculous, and part of the reason that it's not ridiculous is, well, first of all, we'll have models where this can be realized, but the reason it can be realized is that discrete complex analysis already gives you something in the flavor of sort of conformal maps in the continuum. Okay, so that's my first sort of wish on the wish list. I can equip a reasonably defined space of local fields of a discrete model. Of course, I owe you a definition of what I mean by local fields, and I'll come back to that. But on reasonably defined local fields, I'd like to have a representation, well, two commuting representations of Virasoro algebra. Second of all, I'd like to put these in somehow in correspondence, the fields of a CFT with the fields of a lattice model. The most naive thing you could hope for is that, to every locally defined random variable, I can assign a local field in a CFT, and to every local field in a CFT, I can find a locally defined random variable. So I have one-to-one correspondence. I'm going to be exactly that naive. And moreover, if dream one is realized, I can ask this one-to-one correspondence to be an isomorphism of representations of two Virasoro algebras. So that's my wish two. And the last one what do we do with local fields is we take correlation functions. So we should relate those correlation functions in some sense as the lattice mesh goes to 0, and my discrete domains omega delta approximate the continuous domains omega in the reasonable sense. Now, as you can tell from the earlier examples there, you certainly need to renormalize in some sense. I should say, one thing is, in order to make this, I already needed the correspondence, the one-to-one of my wish two, because I want, of course, that when I insert one field here, I know exactly which conformal field theory field I should put on that side. So I needed the correspondence of wish two in order to make sense of the wish three, which is the convergence. And I'll, of course, need to renormalize. And if I had my wish one, which was the Virasoro actions, there is the the obviously right way to renormalize, which is by the L0 plus L0 bar eigenvalues. So I should say minus L0 plus L0 bar eigenvalue. So I'm being slightly sloppy because I should, of course, assume that my fields here were L0 plus L0 bar eigenfields, and I should take the L0 plus L0 eigenvalues for every field and then add them up. But schematically, this is what I want in the width 3. Okay, so now that's my wish list of what it means to describe a statistical mechanics model by a conformal field theory. Do you think I'm not requiring enough, or am I requiring too much? Would somebody want more or less? Yeah.
You want to converge to some CFT on the right?
Yeah.
And the state space, you think of it as a Hilbert space and representation of the Yazo and so on? Or do you want really continuous random variable on the domain omega?
So I took the rather algebraic point of view that I just have a vector space with two Virasoro algebra actions. Okay, maybe actually modules for VOAs, so that I can talk about conformal blocks and I can make sense of this aspect here in the spirit of what, for instance, we described last week, etc. So rather algebraic, actually.
But there is also the question of converging to some random variable.
There's the question of conversion to some random variable. I'm sort of for making sense of CFTs as a scaling limit. I think the algebraic approach to CFTs is, in my opinion, the clearest. So therefore, I'm taking the purely algebraic approach for the CFT side.
I think points 1 and 2 cannot possibly work because you are discrete. So you have to at least do some funny quotient, something to your space of lattice observables.
Yes. Yeah. So I think a reasonable objection is that I'm actually requiring too much. Because but at least nobody is saying I'm requiring maybe too little. Good.
The Ising case, right? You already know that the correlators of the Ising model satisfy the consistency conditions you would want of a system of correlators, right? So they would be compatible with factorization because they're already the Ising correlators. But if you start from an arbitrary lattice model, then you get some collection of functions. And so far your approach doesn't give you that these satisfy factorization in CFT line.
Yeah. And for the Ising, I mean, I want to make a remark that these results say for two particular local fields. Yeah, I want to make one important remark I want to make is that I required these for all local fields. So where do I make the remark? Yeah, maybe I make the remark here. So this is an important remark. So primary fields are a strict subset of all local fields. So you could say that these were actually sort of results for scaling limits of the things that you'd expect to be primary fields in the Ising model. And similarly, I'm saying that sigma of z and this sigma z plus delta minus 1 over root 2 is a strict subset of all locally defined random variables. So what I want here is like much more than this. It's an infinite dimensional space of local fields in the Ising model. There are just two primary fields. Okay, 3 if you count the identity. So I want infinitely more here. I want clearly infinitely more here. I could take the product of 3. I could take the product of 3, subtract the product of just 1 with the right coefficient, so to cancel the leading order sort of scaling limit behavior, etc. So I want infinitely more than is in these results. Okay. Yeah.
I'm worried that for anything more complicated than an Ising model, it will be very complicated to disentangle different primary fields if they transform in the same way under the global symmetry. For example, if you had several energy operators, like in a tricritical Ising model, something like this. It would be hard to realize on the lattice something that would just be purely one of them and not mix them.
Yeah. Okay, so I agree that probably these dreams. So these can be realized for at least partially for at least 3 different models. So I think that's an indication that these are not completely unreasonable dreams for at least some very integrable models. But I agree with that maybe in that strong a form, these might only be feasible for rather integrable models. Anyway, so the Ising model, we'd like to know the scaling limit of the Ising model being described by conformal field theory, wouldn't we? So, yeah. So that's like, I'd want a theorem that states that.
Sorry, you want a theorem that states what?
That the scaling limit of the Ising model is a conformal field theory. And this would be sort of the 3 things that I think it should contain. Yeah.
I asked a question like numerically, if I remember well, when you do a finite size effect on correlation function on Ising, some finite size effect next to leading order, like you can see some exponents which are outside the cast table. So in some way, the lattice can contain also a little like more than the minimal model.
That's an excellent point. So this correspondence will definitely depend on what you allow as the fields. So I haven't. So as I said, I owe you the definition of locally defined random sort of local fields in my discrete model, and actually some choices that go into there, which is sort of what are the the probabilistic questions that you allow yourself to ask. That is a choice that goes into what do I mean by scaling limit. That definitely goes into here, and I will take a particular choice, whether that's restricting and not allowing certain questions. That's very much possible. Some choices go into here, but some choices go into what we mean by this notion of scaling limit. Certainly, yeah.
Quick comment on that. I think that that's a gap. I'm taking your time away. That's a gap in the formalization of CFT, which is what is the correct algebraic description of like cluster boundary observables on the lattice side. That's like a global question, which in the Ising model will give you log correlators. And I do not know what is the sort of algebraic framework to put this on the right-hand side.
Yeah. And probably exactly since I take locally defined in terms of the underlying configuration of local degrees of freedom, I will not capture exactly those. So this is certainly just one way of looking at it, but yeah. All right. So I wanted to say that these are not completely outrageous dreams. So for instance, these are realized in 3 different models. So let me just make a quick summary. So at least what is currently known about this. There are dreams, sort of wishes 1, 2, and 3. And there are some models that you might know about, let's say the Ising. Okay, so this one was done, work published in 22 by Clement Honger, Fredrik Wiklund, and myself. And maybe I should sort of indicate that, yeah, there's a central charge of the CFT and the Virasoro representations, and the central charge of the Virasoro representations was 1/2 for the Ising model. Maybe not a big shock to anyone who has heard about, but it's indeed, yeah, a theorem now. Well, for a certain notion of local fields. There's a different one, discrete Gaussian free field, which I'll define in a moment. That was also done in the same paper. So here the central charge was 1. There's a third one, kind of discrete symplectic fermions in a lattice model of double dimers So that was done by David Adame Carrillo in, I think, 23. Okay, and the central charge here is -2. So there are 3 models in which my dream one, or which one is actually realized. It's completely fair point that this might not extend to models that are not extremely integrable, but at least 3 models that exist. Now, the only model for which published theorems exist for which do dreams 1, 2, and 3 is the simplest model of discrete Gaussian free field. So with David and Della Behzad and okay, we have the wish through to realize the identification of one-to-one correspondence between the fields and the scaling limits. So with 3 scaling limits with the renormalization by L0 plus L0 bar eigenvalues also realized for the discrete Gaussian free field. Actually, here I should say for the gradient of the discrete Gaussian free field, and that pertains to exactly what are the allowed questions that you allow yourself to ask about the probabilistic model. Now, there is work in progress for, but not written up yet, for using with Chelkak, Isurov, and myself. So I will, yeah, I mean, not written up yet, but the using case should be done soon. Maybe the slightly interesting one is this one. I think there is work in progress by David on this one. And let me emphasize that this is actually a model where we know that L0 will not be diagonalizable. This is actually going to be a logarithmic conformal field theory. I think it's extremely nice to have a discrete model of a logarithmic conformal field theory where you have the Virasoro representation on the discrete local fields. Probably you'll need to modify the renormalization by L0 plus L0 bar eigenvalues if L0 is not diagonalizable. So maybe there are logarithms in the renormalization that are needed in that case. Okay, yeah, and maybe this my construction gives full CFT, so maybe in the theme of the workshop or the conference, those works in progress are an interesting thing to note. I realized that I've been a lot slower than I wanted, but the goals make sense? I wanted to then define precisely. So I definitely owe you the definition of local fields, especially. I wanted to also, since the results are complete for this slightly simpler model of discrete Gaussian free field, I wanted to actually define that model. And also, I think it's useful to have 2 models so that we see clearly in the results which parts of the results are model dependent and which aspects are sort of the same for all models. I'm going to define the discrete Gaussian free field. So DGFF, discrete Gaussian free field. I'm not going to write that the second time in the talk, so DGFF is going to stand for that. I'm going to define it again only for Dirichlet boundary conditions for simplicity. I care about being able to define something with Neumann boundary conditions as well, but I will not fully write that down on the blackboard. So this is a random height configuration, if you wish. Similarly to how Ising was a random spin configuration, so that's a phi. For every lattice side Z, you assign a real valued random variable. And let me just say that the probability of phi has density, which is up to a normalizing constant, density with respect to Lebesgue. So d phi setting delta. And the density is exponential in my normalization 1/8 pi times the discrete Dirichlet energy of the configuration. So here d phi is the sum over nearest neighbor points on my discrete domain, nearest neighbors of the squared difference of those things. And then I need to put Dirichlet boundary conditions. So I'm summing over points in the domain, which are neighbors to points outside of the domain, just putting phi of z minus 0 squared. So I'm sort of pretending that the values of the field outside of my domain are 0. So that's the Dirichlet boundary condition. So this was the Dirichlet boundary condition. All right, well, makes sense. Maybe I'll give one example of a local field here. So I could take this thing. So this is kind of a horizontal derivative squared plus, let me take a vertical derivative squared. So then this would be kind of a gradient squared. Discrete gradient squared. Now, for this local field, does anyone have a guess, for instance, by what I should renormalize? So I needed the L0 plus L0 bar eigenvalues to renormalize correlation functions. So any proposals? I should admit that this is a trick question, but otherwise I wouldn't be asking. Right? But any proposals? 2 is exactly the answer that I was hoping for, which is to the trick question, because this is the gradient squared. You'd imagine that you'd need to divide by delta here for a meaningful scaling limit. So the point is, just like in the Ising model, in order to actually have L0 plus L0 bar eigenvalue, you'll need to I mean, if you didn't do anything, this would diverge if you would divide by delta squared. But if you sort of add the right constant and then divide by delta squared, then this converges in the scaling limit. So this will converge with delta to the minus 2 renormalization. So finding the exact L0 plus L0 bar eigenfields, you'll need to do something. But here's an example. Okay. Yeah. Okay. So then this would be somehow first of all, regularized and renormalized gradient squared of the free field. Okay. Right. I did want to say that one can impose Neumann boundary conditions. Kind of, except that then the field values don't make sense as such, but they will be well-defined modular and additive constant. But for instance, for the differences of the free field, that will make sense. And that's kind of why I will consider the gradient of the free field. So I will consider just the process of Gaussian process of differences. Okay, I'm not gonna write down the precise definition, but one can define something meaningful, but it will not have, it will have an additive constant ambiguity. And I still want to consider the same local fields for both Dirichlet and Neumann. Yeah.
Can you make this work if you make the field take values in some compact lattice? Some compact, I mean not lattice, some quotient of R.
Yeah, it's an interesting question. So first of all, would you want to modify? So one can of course take this and mod out something, and if I have a random variable taking values in R, I can mod out R by something, or I could take multiple components and mod out by a lattice. But did you maybe simultaneously want to modify the action or the allowed field configurations? Maybe you wanted to allow for monodromies in the field configurations, and I think I won't say much more, but depending on what you mean, yes, maybe. Yeah. Yeah, okay, so I'm really actually out of time. Oof. Oh gosh, I didn't even get to the definition of local fields. Should really try to, so how much time do I have?
10 minutes maybe.
Okay, I'll really try to, okay, sorry. I'll try to define local fields at least. That's the main thing I owe you the definition of. Yeah. Oh no, okay, yeah. Yeah, so that's the main thing. So yeah, I claim that these 1, 2, and 3 are theorems, for instance, for the discrete Gaussian free field with the right definition of local fields, but now I definitely need to give you the definition of local fields. Trying to get through that at least. Right, so the idea is that there should be local fields supposed to be something, a translation invariance rule that allows you to produce random variables. Somehow, depending on only finitely many degrees of freedom locally. So you take some finite subset of points on the lattice, and then a function depending on those, and you apply that function to your local configuration. Okay, so it will be an abstract local field polynomial. Which then in any given domain and with any given lattice mesh, so maybe there is some one discrete domain or a completely different discrete domain with a completely different lattice mesh, so maybe a really fine lattice mesh. Okay, and any point in the domain Z where I want to insert this local field. So then I should be able to produce a concrete random variable by somehow evaluating the abstract local field polynomial. So evaluation. One of the reasons I wanted to give you two different models is that the definition of abstract local field polynomials and the evaluation does depend on the model. So I'll give the definitions for both the Ising model and the discrete Gaussian free field. So for the Ising model, my local field polynomials are the formal span of finite subsets. Let's say S of the unit mesh square grid. So okay, I want to use the unit mesh square grid here. I produce random variables with whatever small lattice mesh in whatever domain at whatever point. And the evaluation in omega delta of let's say such a subset, finite subset, will produce the random variable in my Ising model, which is the product over points in my finite subset of the spin located at my point Z shifted by U points here tell me how many lattice units I'm going to move around, pretending that Z is my origin. And the discrete Gaussian free field gradient local field polynomials is the space of polynomials in infinitely many indeterminates indexed by the unit mesh square grid, where the evaluation takes, this is, by the way, of course, linearly extended to the formal span. The evaluation of a monomial is such that kind of an individual variable here became the field at Z shifted by uj lattice units, but I want to only consider differences of field values. So I'm subtracting the field value at exactly Z, and now these local fields make sense both with Neumann boundary conditions and with Dirichlet boundary conditions. And since it's only allowing differences, I'm calling these the gradient of the discrete Gaussian free field local fields. Okay, so these are my definition of local field polynomials. Now there's one really crucial thing that needs to be done. There are some local field polynomials, some non-zero local field polynomials, which don't have any non-zero correlation functions with anything that is not only microscopically separated. I don't think I said that very clearly. Let me try again. So there's some local field polynomials whose correlation functions vanish except for really when you probe at microscopic distances. There's a notion of null fields. Let me define that for Ising model. So it's a subspace of field polynomials for the Ising model defined by the following condition. So I say that N is a null field for the Ising model if, so this is the definition, for all, so there exists a finite number R such that for all lattice mesh sizes, for all discrete domains, omega delta, such that, and now I need the macroscopic separation, so or non-microscopic separation, such that so distance of, I should say, for all points Z in my discrete domain, such that the distance from Z to the complement of the domain or the boundary of the domain is at least R lattice units, and for all other points W, Wn, such that distance of Z to W is also at least R lattice units. A lot of quantifiers. I want that in this situation, the evaluation of the local field at Z with any product of spins at those points Wj's is literally zero. Actually, I forgot one quantifier. This is also for all boundary conditions that I allow. So for a lot of quantifiers. So that's that type of a field I would call null. I wanted to give an example, but since I'm really running out of time, I'll maybe say the example for later, and now I can maybe state the theorems. So theorem 1 for, let's say, the discrete Gaussian free field. So this is Unger, Wiklund, and myself. So I'll state this for the discrete Gaussian free field. So there exists operators. So I forgot. So these are null fields, and now what we want to do is we want to mod out by those. So we only want to consider fields modulo fields which you can't see in non-microscopic correlation functions. I'm going to define F easing to be the polynomials modulo the null. And I should give a completely analogous definition for the discrete Gaussian phi field and define F discrete Gaussian phi field. Gradient of the discrete Gaussian phi field is that space of polynomials modulo null fields similarly defined. So these are the spaces of local fields, equivalence classes of locally defined random variables. And now there are operators ln bar from my space of local fields of the gradient of the discrete Gaussian phi field to itself. And ranges over integers such that LM commutation relation is exactly the Virasoro commutation relation. Similar for LN bars. And LN's commuting with LM bars and where C is equal to 1. So that's the realization of the first wish. And if you were to modify these to the easing, then you'd have basically the same exact C equals 1/2. So those are the realization of the wish 1 for both models. And I should state that I'm really out of time. So maybe I will state only in words without writing anything. So theorem 2 for the discrete Gaussian phi field says that this space is isomorphic as representation of Virasoro algebra with the chargeless Fock space in 2 chiralities. For the Heisenberg algebra. Charge 0, 2 chiral Fock space. Isomorphism as representations of Virasoro algebra because we know by theorem 1 already have a Virasoro action. And theorem 3 would be that if your domains, okay, one thing that this theorem 2 then gives is because on the chargeless Fock space, L0 and L0 bar are diagonalizable, which is not obvious that they would be diagonalizable on this space of local fields. But once I know that this is isomorphic to the 2 chiral Fock space, I know that L0 and L0 bar are diagonalizable. So every local field is a finite linear combination of L0, L0 bar joint eigen fields. And if I now take a scaling limit where my discrete domains approximate in category sense, I renormalize by the L0 plus L0 bar eigenvalues, then I have convergence. Okay. But I think I can't even state the theorem in the time it remains. So maybe I'll stop here.
That's nice. So also for the easing case of representations.
Yeah, so that's not written in the literature, but so that's work in progress with Chalkak and Isuro. So yes, and you do see exactly this full CFT 2, diagonally paired 3 irreducible highest weight representations. Yes,
That's very
but yes, so it's not yet written up.
Regarding theorem 1, like you stated, there exist operators that are Virasoro type. Are they exact even on a lattice scale, or do you take some sort of scaling limits?
Yeah, I mean, these are literally on that space. So what I took is the field polynomials modulo null fields. Exact on the lattice. Now that might seem indeed surprising. So maybe should I say something about that? Yeah, it's kind of important in which order quantifiers are. So if I take a given local field, it requires some finite lattice neighborhood around the point of insertion to produce a random variable. So of course, in order for that to make sense as a random variable, you need to take a big enough domain. So in particular, when I pass to the scaling limit, any bulk point will have an increasingly large lattice neighborhood around it. But you might need to take a small lattice mesh for a given local field to make sense.
So, as far as I know, there is this lattice construction of Virasoro generators called the Kalle formula. So, do you think they're related or they're independent constructions?
Yes, that was certainly a part of the inspiration. I'm not exactly sure these are related. Yeah, maybe I should have said this construction goes via first constructing something, basically Heisenberg algebra action. And the reason it goes via that is that the Heisenberg algebra is built out of a current of the free field. And the current actually has better discrete complex analysis properties than, we don't have actually a discrete holomorphic stress tensor. One actually goes via currents to produce this. That applies to Sugawara construction. Similarly for using one goes via kind of fermionic currents. And an individual fermion will not make sense as local fields, but a pair of fermions does. And we only need pairs of fermions for the Sugawara construction.
We know loss equals -2.
Yeah, so we know that in double dimers there are meaningful local fields, a little bit complicated to define. They are weighted existence of double dimer paths, which again similarly define local field polynomials, and you can quotient out null fields, and there is a representation at C equals -2 for those local fields. I am sure that David can prove that, for instance, on that space, L0 and L0 bar are not diagonalizable. The exact isomorphism with a CFT state space has not been proven.
Do you know like the beta number? The beta number for the stagger?
So I think David has seen only representation which has the logarithmic partner is at equal highest weight. So there is no non-trivial logarithmic coupling to compute in that situation. Yeah.
Can you also include boundary fields in this setup?
That's a very good question. One thing that I should say that one important thing that the lattice did, it sort of told me how every point in the domain looks similar to every other point. So now I need every lattice point to look similar to every other lattice point. So maybe I should take boundaries that are on a macroscopic scale, let's say parallel to a coordinate axis, in order for my lattice, in order to be able to locally identify. Yeah, by the way, so I think the lattice kind of played the role of a local coordinate. And one thing I didn't say is that in the conformal blocks, which I think everybody here knows depend on local coordinates, I should have taken the identity local coordinates provided by the inclusion of my domain to the plane. Okay. So yeah, one thing that the lattice provides is a local coordinate, and you want the same thing on the lattice, and maybe that you should restrict attention to when the lattices are straight coordinate axis directions. Yeah, I think again, David Adamacarrillo has some results in that direction. I'm not exactly sure to what extent things are fully understood, but there are some results making sense of that, but with the limitations of only straight boundaries, vertical or horizontal on the square grid, etc.
For the easing case, Don't you have problem with like domains or because these are unbounded operators, these LN?
Yeah, I mean, so I put no topology on my vector spaces of local fields. So these are I mean, yes, their eigenvalues, for instance, are unbounded, sure. But everybody is a finite linear combination of, for instance, in this space, after proving theorem 2, I know that every such local field is a finite linear combination of eigenvectors. I put no topology, no functional analysis. This is pure algebra.
More questions? Maybe we should thank Kalle again. We start
15 minutes, 11:30.
11:30.